This is Lab 3, Black Hole Orbit. The point of this lab was to find the mass of a black hole using position data of a star of unknown mass that was orbiting the black hole. I quantified the motion of the star to determine the mass of the black hole and analyzed the relationship between various forces and changes in momentum. The motion of the star was analyzed with a model programmed in VIDLE using data from a file provided. By applying Newton's gravitational force principle and using the connections between the different FNet components and the dp/dt components, the mass of the black hole was determined to be 3.98 times 10 to the 31 kilograms. The two main principles that are applicable to this lab are the momentum principle and Newton's law of universal gravitation. The momentum principle states that the change in momentum is equal to the net force acting on an object times the duration of the interaction. The momentum principle breaks down change in momentum into a parallel component and a perpendicular component. Newton's law of universal gravitation states that there is a force of attraction between all masses in the universe. This force is quantified by the equation force of gravity equals gravitational constant times the mass of object 1 times the mass of object 2 divided by the distance squared, then multiplied by negative r hat. This force is directly proportional to the product of the masses of the objects and inversely proportional to the square of the distance between them. To create my model, I used the initial conditions that were given to me. Here I have the mass of the star, which is 1.989 times 10 to the 30th kilograms, the location of the black hole, which is 4 times 10 to the 10th, negative 5 times 10 to the 10th, and 0 meters, and the change in time, which is 1 day or 84,600 seconds. These, as well as a CSV file holding the position data of the star, were provided. Here, the model takes in the data from the CSV file. The first while loop uses the position data to compute the velocity of the star during each time interval as it moves around the black hole. In the second while loop, the initial and final velocities just calculated are used to compute the initial and final momentums of the star by multiplying the star's mass times the respective velocity. These values can be used to compute delta V and delta P. dp/dt is then calculated by setting it equal to the change in momentum over the change in velocity. According to the momentum principle, Fnet equals dp/dt, so we set Fnet equal to this value. Then I calculated p hat, which is the direction of the momentum, by dividing initial momentum by the magnitude of the initial momentum. Using that, I found the magnitude of dp/dt parallel because it is the change in magnitude of the momentum divided by delta t. I then multiplied that by p hat to get the parallel component of dp/dt, which is equal to the parallel component of Fnet. To find the perpendicular component, I subtracted dp/dt parallel from dp/dt because the change in momentum is the sum of its parallel and perpendicular components. Like before, the perpendicular component of the net force is equal to the perpendicular component of the change in momentum because of the momentum principle. I will now demonstrate the model that is generated when I run the code. Here, the orbit of the star around the black hole is being shown. The yellow arrow represents the net force, the blue arrow represents the perpendicular component of the net force, and the black arrow represents the parallel component of the net force. To solve the mass of the black hole, I used Newton's law of universal gravitation that was discussed earlier. That formula is shown in these lines of code. Because the net force was already known, I rearranged the equation to solve for the mass of the black hole. When the code is run, the value equated here is printed in the shell, which gave me a value of 3.98 times 10 to the 31 kilograms. I will now move on to the discussion questions. The first question asks for a discussion of the differences between Fnet, its parallel component, in the perpendicular component, and dp dt its parallel component in its perpendicular component. They are different in the way that they are calculated. In this case, F net is the force of gravity, which is calculated using the equation that quantifies Newton's law of universal gravitation. On the other hand, the change in momentum is derived using another calculation, using change in velocities, or mass times acceleration. The net force can be calculated by adding up all forces acting on the object, while dp dt is found by observing the motion of the object. At the same time, only the net force can actually affect the object's motion. Even though the momentum principle states that these values are equal, they are different because they are found in different ways. The next question asks, if the current black hole was replaced by a different black hole in the same location, but the motion of the star did not change, could I detect the change? Because the data is unchanged, there is no new gravitational force, and every value in the equation that derives the mass of the black hole is also unchanged. Therefore, we cannot detect the difference.